SwayamPrabha. Digital India. Educated India.
So, in the previous class, I spoke about the eyelids technique, which is a planar technique for measurement of particle size. The particles must be transparent and spherical. So, these are the conditions. And we have seen the advantages and limitations of this technique, and then we saw how the eyelids technique can be combined with PIV technique, which is also a planar technique, and this facilitates measurement of various vital two-phase statistics. So, similarly, eyelids can be combined with LIF, as I also mentioned in the previous class, for measurement of vapor concentration around the droplets along with the droplet characteristics. So, in this case, as you can see here, two different lasers are used. One is for eyelids and one for laser induced fluorescence or LIF technique. We are calling it as planar laser induced fluorescence technique because here we create a laser sheet which is combined with the laser sheet from the green laser. So, the 532 nanometer or green light is used for eyelids, while 266 nanometer or UV light is used for LIF. So, this was applied to an acetone spray. So, in case of acetone, the acetone droplets would fluoresce as well as the vapor of the droplets. So, both fluoresces. Now, what do we achieve by this is that we can measure particle size, velocity and concentration from eyelids and vapor concentration in the vicinity of individual droplets from LIF at the same time, at the same location. Here also we need two different cameras. So, as you can see here, the eyelids camera, because here we have to arrange the eyelids camera at some scattering angle. So, this is a non-90 degree view as usual for the eyelids camera. However, for LIF it is the viewing angle is 90 degree. So, both cameras must look at the same location, and this is achieved by using a target plate or a calibration plate before starting the experiment. So, you have to map the viewing area observed by both cameras. You have to map them to the same object plane. Okay. And so, this shows the image processing. So, as I mentioned, here you have two different kind of images. So, first you process the eyelids image, then you process the LIF image. Now, we can remove the droplets from the LIF image because in this case the acetone droplets as well as acetone vapor, both of them fluoresce as we excite them with the UV light. So, we will see fluorescence from both. However, our target is to measure vapor concentration. So, we have to remove the contributions from droplets, and that is what is done here. But we know the droplet position and size from eyelids. So, that is how we combine, and finally, as you can see in this example, we get the particle size which is shown as circles of different size, particle velocity and also the concentration around particles. So, now similar to combined eyelids PIV technique, in this case also we get many we can get many important two-phase statistics. Now, the application of this combined LIF technique is shown here for the acetone spray. So, we can measure the size distribution, and also as in the previous class, here we can divide the droplets into different size classes, and we can calculate the Stokes number for each size class to see how they respond to the turbulent flow fluctuations. And we can first measure the mean characteristics. For example, as you can see here, the SMD is shown, and for comparison purpose, measurements were also taken using a water spray. So, if you use a water spray, then you do not measure the vapor. It is not like water does not have vapor, water also has vapor, but the here measurements were obtained for water case only using the eyelids technique to measure the spray characteristics. So, you can see the difference between the water spray and the acetone spray when they were operated using the same injector under the same operating conditions. So, the operating condition, that is the fluid flow rates, are kept same for both cases. And now we see a difference. For example, the water spray case, the SMD does not vary in the radial location, where the measurements are taken at certain axial location downstream of the injector exit. So, in radially the droplet size does not vary, but it decreases in case of the acetone spray. And this is the plot for number density. What happens to the mean number density when we look at the water spray and the acetone spray? The number density, as you can see, it reduces significantly, and also for both cases it reduces towards the edge of the spray. And what happens to the fluctuations of the number density, that also we can measure, and here we see that the fluctuations increase towards the edge of the spray. And this is the vector plot for the droplet velocity, 15 to 30 micron droplet velocity, and you can get this for different size classes also. So, I am showing these results to give you a flavor of the kind of data that we can obtain and how we can use those to understand the physics. And this is the mean vapor mass concentration. So, if you see the mean quantities, they are as expected, but this also in a way tells you that your technique works as expected. That is, here you see that the mean droplet velocity reduces towards the edge of the spray, and in this case you have a solid cone spray. So, where you expect the droplet velocity to be high at the center and it should reduce. So, we get the behavior as expected. Similarly, the vapor concentration is high at the center of the spray and it reduces towards the edge of the spray. And this slide shows now the unsteady dynamics part. That is, this slide shows the scatter plot between the vapor concentration and the number count at a particular location at any instant. So, each point here refers to one instant of time. So, at that instant of time, at that location, what happens to the vapor concentration or vapor mass fraction as droplet number count say increases, and overall you see that as the number of droplets increase, the vapor mass fraction also increase. So, you can say that okay, this is also expected. Why? Because the more the number of droplets, the total, if you see the total gasification rate or total vaporization rate is high accordingly, and that is why the vapor concentration is high. But then if you see along say this line, here you see that you get the same vapor mass fraction in this location, whether you have 10 droplets or 70 droplets or say 60, 70 droplets. Now, why would that happen? And this happens because of the scatter of the data. Overall, you see more or less there is a linear trend, but what causes this scatter of data. So, similarly along this line you see that even if you have same number of particles or same number of droplets, the vapor mass fraction varies significantly. Now, what would cause this? That is the question. An attempt has been made to calculate the correlation between the number density fluctuations and the vapor fluctuation. So, how are they correlated? So, this means that if the fluctuation in the number density is say positive, then what happens to the vapor fraction? Should it be positive? Now, you can say, okay, why not? Why the fluctuation in the number density should not positively correlate with fluctuation in the vapor? This is because the reason behind this is because the slip velocity between the droplet and the vapor. So, a droplet is moving and at the same time it is evaporating. Now, the vapor which is generated, will it move at the same velocity? So, if not, then what will happen? Now, you are looking at the same area and at any instant of time you see the droplets here, but the vapor you see here may correspond to the droplets which has already passed this area. Okay, that is possible. So, this can cause some decorrelation between the number density fluctuation and the vapor fluctuation, and that is what we see here. And you see that this correlation is quite strong when we consider 50 to 30 micron droplet or small droplets. But as you go on increasing the droplet size or higher the size class, lower is this correlation. Now, what causes this? Why do we see this? This is because of the relative velocity between the vapor and the droplet. Now, you can ask, should the vapor also move with the same velocity as the other phase? What is the other phase here? Not other phase, other component, air. So, in this case you have a simple evaporating spray of acetone. So, in the gas phase now you have two components. What are those? Vapor and the air. Should the vapor also move with the same velocity as the air? It depends on the density of the vapor itself. Should the vapor density be equal to the air density? If yes, then they will move at the same speed. And the other factor which governs this is the local vapor mass fraction. So, finally the gas velocity at any point of time is, you can say, it is a weighted average of the velocity of the vapor and that of the air. Okay, so we can also calculate the group number that we have already discussed earlier. So, group number is a non-dimensional number that tells us how strong is the group effect. Group effect means if the droplets are close to each other, then they influence the droplet vaporization rate, and the overall vaporization rate of a cloud of a droplet, as in the case of droplet clusters, can be significantly smaller than the evaporation rate of a individual droplet. And this may be linked to the observation, earlier observation that I presented, that the vapor concentration or vapor mass fraction at the same location differs significantly when the even if the number count is same. When that can happen is if you have different separation distance between the droplet, or you can put it in other words, if a cluster of droplets passes through, then at that time we can expect the vapor concentration to go down. Okay. So, that is the reason why it is important to see what is the magnitude of this group number. Okay. And this can also be calculated. So here you can see some clusters which are qualitatively shown, but this agrees well with the size of the clusters which is calculated using the radial distribution function. I am not going detail into that, we will see that later. And here finally the group number is shown here, and you see that the group number is between 0.5 to 1 around. So this means that you have internal group evaporation mode. Okay. So the group number is not very high, I mean it is not beyond much beyond 1, but still you see this effect, the group effect is present, and that is why we see such observations as this scatter in the distribution of vapor concentration and the number density. So now we will look at another planar droplet sizing technique which is known as PDS or planar droplet sizing technique. This is also known as lift-me technique. Why? We will see this. So in this case the principle is that we add some fluorescent dye, for example rhodamine 6G, to the liquid. So this is meant mainly for sprays, for spray measurement. Then we excite that through a laser, let us say green laser or 532 nanometer. So the green laser, because of the green laser, the droplets would scatter light, which is me-scattering. But at the same time, because we have added a dye, the dye will also fluoresce, and we can capture the fluorescence light distinctly because the wavelength of the fluorescence light is red shifted, which means that it will be around 550 in this case if you use rhodamine dye, rhodamine 6G. Then by putting suitable filter, we can capture the fluorescence image only. So by using two cameras, we can capture the me-scattering image, which is actually proportional to d square. Okay. This is the me-scattering image is proportional to d square, while the lift intensity is proportional to the volume of the droplet. It is a volumetric technique. Why? Volumetric emission technique, which means that while the scattering occurs only from the surface of a particle, laser induced fluorescence or fluorescence occurs through the volume. So the emission occurs from the volume. That is why it is proportional to d cube, while in case of me images, the intensity is proportional to d square. So the idea is that if we look at the same location using two cameras, in one camera I have me and the other camera I have lift signal, then the ratio should give me SMD directly, or the Sauter wind diameter. So basically the SMD is proportional to the ratio between the lift signal and the me scattering signal through and we have a constant here, a calibration constant. Okay. So here you can see the images. So this is one is the me image, one is the lift image, and we take the ratio and we directly get plot for SMD. So using this technique, you can't measure individual droplet size, but you can directly measure the SMD. So this is useful for the case where you have higher number density in your flow, or you can say close to the injector exit. Okay. So we can use this technique. However, so basically the advantages of this technique is that it is non-intrusive, we can get 2D temporally resolved data. That is, if you use a high speed laser, Okay. Then you can get this data which is temporarily resolved or time resolved also. Then we get spatial map of the SMD, and it can work in dense space where individual droplets cannot be resolved. So, in such cases, means when we have high number density, we cannot use eyelids or PDP. So, in that case, this can give valuable information. However, the limitation is that, okay, we can get only characteristic droplet size, and unfortunately, the calibration constant, okay, is dependent on several factors. Okay, so it is not a universal constant. Okay, why? Because of this reason. So you see, the fluorescence intensity, which is volumetric in nature, it is also isotropic. So you see this orange color. This is isotropic. Means the intensity won't vary with the angle or scattering angle. However, scattering intensity is not like that, as we have seen earlier also. You see lots of fluctuations around the particle. Okay. So, this calibration constant would depend on the scattering angle. At what angle you are positioning the camera. Okay. It will also depend on the optics you are using, the refractive index, the dye concentration, wavelength, polarization, and response of the detector as well. So, this means that the you have to do the calibration under identical optical flow conditions. This means that before you use it in your spray, you have to use some kind of spray where you know the droplet size distribution or the droplet size, and then use this technique, get the leaf intensity, mean intensity, take the ratio, and from there you calculate what is the calibration constant. Okay. And once you do that, then under the same optical conditions, means then you should not change your optical configuration. You should keep it as it is and then use the spray. And there are other issues, practical issues, like it is sensitive to fluorescence quenching and laser attenuation. Now, what is fluorescence quenching is that as light passes through the droplet, then some of the light is also absorbed due to the fluorescence dye you are using. So, the fluorescence dye, obviously it absorbs light and it emits, but partly is completely absorbed. It is not like the light it emits is equal to the light it absorbed. So, that is the problem. So, that is why the laser intensity itself reduces even within a droplet or past a droplet. So, especially if there is a large droplet in any lift technique, even in the previous planar lift that we discussed, there we have seen that past a large droplet, you can see a shadow of light, and that is because the light is being absorbed by the droplet, okay, because you have added a fluorescence dye. The next technique is shadow imaging technique, and if we use a high speed camera, then it is called high speed shadow imaging technique. But it can be in general called shadow imaging technique. Sometimes people call it as shadow graph technique also, but to differentiate this from an actual shadow graph image, which refers to double derivative of density in a flow, like in case of Schlieren, which gives us single derivative. Similarly, shadow graph in actual sense gives us double derivative. However, here we are not referring to that. So, the main advantage of this technique is its simplicity. So, you have a flow, you put a backlight So you back illuminate the flow. Back illuminate means your camera and your light source are in opposite direction. You back illuminate a flow and capture images. And then using image processing, measure the size. So it sounds very simple, but unfortunately this is also not. But the optical configuration is definitely simple. So it does not involve any special source of light. Though sometimes laser is also used, but instead of that a strobe light can be used, which gives us pulsed light. So as you can see here, the photographs in a spray. Okay, so you can look at different locations starting from the injector exit to downstream. Now, there are some considerations, of course. One can ask, okay, what if we use a continuous light source? Yes, you can use, but in that case, the exposure time of your camera to capture one frame has to be very small, such that the flow field is freezed, such that you avoid seeing streaks of particle. Okay. Otherwise, a very good way is to use a strobe light, which itself gives pulsed light, or you can also use a pulsed laser to illuminate the flow. Now, the advantage with that is you will see the flow only when you have a laser pulse, or in case of strobe also. So, and that pulse duration is usually very small, of the order of few nanoseconds. So, you actually freeze the flow and it becomes independent of the exposure time of your camera. So, that is the advantage. And yes, so the exposure time is decided by source duration, flow time scale. So, basically faster the flow, the exposure time has to be smaller. So, if you use this technique, let us say for particles in supersonic flow. So, as of now we haven't discussed this. Okay. So, this has application, for example, in scramjets. So, you have droplets in supersonic flow. So, if you want to capture particles in such a scenario, the exposure time has to be really very small. And of course, camera resolution is very important. Why? Because here you see, here if you want to measure size of a particle, then camera resolution has to be good enough. Camera resolution means each pixel corresponds to what value in physical dimension. So, that is what is called camera resolution. So, if you are having a particle of say size 40 micron, then and your resolution is say 10 micron. So, that is each pixel is 10 micron. So, you need at least 3-4 pixels to identify one particle. So, in that case the sizing accuracy will go down. On the other hand, let us say you have resolution of 3 micron while you are measuring particles of size, let us say 40 micron, then you can very accurately measure the size. But what happens, to achieve very high resolution, we have to go close to the flow field or use lenses such that the viewing area is smaller and smaller. So, by the time you get this kind of resolution, for example 3 micron per pixel, the overall viewing area of your camera would be like few mm, so which is a very small region. So, that is why there is a trade-off between accuracy and the viewing area. And also camera frame rate is important, and finally image processing plays a pivotal role, as in case of all optical techniques. So, this is an example of how we identify and measure particles in shadow imaging technique. So, this is a typical shadow technique, shadow image, and this image you get after you subtract the background. So, before capturing the images, we should always capture the background image. and then you can use some edge detection algorithm, and along with binary image binarization, you can identify the particles like this, and then we can define an equivalent diameter for all particles, even if they are non-spherical. Okay, so this is an advantage here. Even if the particles are non-spherical, you can measure its size. You can define, let us say, circle equivalent diameter from this projected area. So what you see here actually is the projected area of the particles. If you put an additional camera and one or more additional camera, you can do three-dimensional visualization, and in that case you can actually see how the particle look like. For example, let us say this particle, here we do not have any information about the length of this particle in a direction perpendicular to the plane of the paper. So, this you can achieve such imaging if you use more cameras, but obviously in that case it becomes more challenging. Now, the other advantage here is that we can, similar to PIV, here also we can capture images at short time interval to track individual particles. So, this here we have particle tracking, and we can measure the velocity of the particle. Another important consideration here is depth of field correction. Now, the problem here is that the number of particles that you see in your image depends on the depth of field. Depth of field means it is the effective depth over which you actually identify the particles. If a particle is far away from the plane of focus, you won't be able to see it, or even if you are able to see it, you may not be able to identify it. For example, let us say these particles. So, you know that there are particles, but you cannot identify, and even if you identify, you cannot measure the size correctly. So, we must reject those particles. Now, the problem here is that the depth of field is a function of particle size. As we have seen this in the case of laser based techniques also. So, the smaller the particle size, smaller is the depth of field, or it can get defocused as soon as it is little bit out of the plane of focus. However, a large particle would remain focused for a larger depth of field. Now, as a consequence of this, what happens is that when you do image processing, you always tend to reject small particles, because they can be easily out of focus, and you detect more of larger particles, and this can introduce a bias, and this can be taken care by fabricating a target plate or calibration plate like this. And before you do the experiments, you need to do these calibration experiments where you deliberately defocus the calibration plate as shown here. So, you see that this is here, all the circular dots are perfectly focused, but as you move this away from the focal plane, then the smaller ones start to disappear soon, because they have smaller depth of field. So, here you see, as you go on defocusing more and more, you lose out the particle. So, but this is how we can calculate what is the depth of field for particles of a given size, and we can get a calibration curve like this, depth of field versus circle size, and then you incorporate this in your measurement, and you see how the profile has changed here. So, you see this mainly affects the small particles. So, here actually you have more number of small particles, and accordingly your SMD and your AMD or other characteristic particle sizes also change. Okay. So, now how important is this? It depends on the problem that you are identifying. If in your problem, this reduction in size of, let's say, around say 60-70 micron, okay, if it is important, then you have to do this. However, if you grossly want to know, okay, what is the characteristic size, it does not matter whether it is 400 micron or 500 micron, then it is okay not to incorporate. But in general, it is advised that you should incorporate depth of field correction. Okay, so because we know particle size, particle velocity and particle number density, it is possible to calculate other quantities, for example, particle volume or mass flux also. So here you can see how in this example, how the mass flux varies for different operating condition of the injector. And also we can calculate the fluctuations in the mass flux. So mass flux, as we have seen from the beginning of the course, this is a very important quantity because it tells you actually how much of liquid is present in, let's say, in your spray. And measurement of only particle size and particle velocity won't give you this information. So the main advantages of the shadow imaging technique is its simple configuration, and we can get 2D temporally resolved data. It provides spatial map of particle size and velocity, and most importantly, it is suitable for non-spherical, even non-transparent particle. So even if they are non-transparent, so this means that it can be used for liquid as well as for the solid particles. But the limitation is that if the particle size is very small, like below 20 micron, then you see more challenges. So accuracy becomes an issue. Then, as I mentioned, there is always a trade-off between spatial resolution, accuracy and the frame speed, because the high-speed cameras usually they have features that as you increase the camera frame rate, the resolution goes down. So this is a problem. So somewhere there is a trade-off you have to maintain. Then it is limited to dilute loading. So if the particle number density is high, then this suffers from multiple, I won't say scattering, but the light is diffused. So the signal to noise ratio goes down. It is very difficult to identify the particles. The case what I have shown is in a region of a spray where the number density is low. So you can see individual particles distinctly. But if you go towards the injector exit, then it will be very difficult to take measurements. And finally, this technique is not suitable for carrier phase flow measurements. So this is not for two-phase measurements. Okay, this is only to characterize particles. And finally, now we discuss integral methods for particle characterization. So till now, we have seen online methods or in situ methods, means you take measurements in your flow. Here also you can do that, but whatever we have discussed, that refers to local measurement. So at any particular location in the flow, you are measuring particle size, particle velocity or carrier phase characteristics. But there are also other methods like integral methods which provides this information, but in an integrated manner. How? We'll see that. So the most popular one is laser diffraction based particle sizing technique. So as I have discussed earlier, so if you illuminate a particle with a laser or say light source, then at zero scattering angle, it is dominated by diffraction, which means that bending of light. The same phenomena happens in the case of where we send light through a small aperture. You would have encountered this earlier in Young's double slit experiment. So, you create a very small slit or an aperture and allow light to pass through it. Then you see an interference pattern when if you try to image this far away from the slit or the aperture. So, this is called diffraction of light. So, here as you can see, here we do not have aperture, here we have particles rather, but that also causes diffraction. And here if you image, what is interesting here is that if you image this spherical droplet, it creates a diffraction pattern like this. Okay. So, which is basically an interference pattern. And also it depends on the size of the particle. So, here you see this is for 800 nanometer particle, this is for 5 micron particle. So, basically the large particles scatter light predominantly at small angles. So, larger the particle size, the angle is small, while small particles scatter light at larger angles. Now, the diffraction pattern depends on size. So, this is the reason why if we analyze the patterns, we can get the information of size. So, it is again an inverse method. So, you have the diffraction pattern and can you measure the size, and that is what this kind of techniques do. So, the diffraction pattern is obtained if the distance between particles and of the observation plane is large enough. So, this is a condition that has to be met, and this is what is known as Fraunhofer's diffraction principle. So, the place where you image the diffraction pattern must be far off the particle. Now, the question is how do we implement it in a practical case where we have so many particles? What will happen in that case? So, when a laser beam passes through a suspension of aerosol particles or inertial particles, you can say, the particles scatter light at different angles. So, now you do not have one particle, you have many particles, and the angular distribution and intensity of scattered light from the particles are measured by an array of detectors which has multiple rings on its surface. So, here you see this is a laser and you have particles here and you collect light at the forward scattering angle of 0 degree. So, this is something, the arrangement is similar to the shadow imaging technique. Okay. I mean here you capture the light pattern, but in the case of shadow imaging technique you capture the particle image directly. So, now here you have a detector which is a photodetector which captures this diffraction pattern, but now what happens, you have, so this one actually this detector array looks like this, similar to the diffraction pattern. So, this is the photodetector. So, you have a band here and this goes on. So, this is the photodetector. It has multiple rings and each ring now captures light from different particles because there are many particles. So, you can imagine there is superposition of the diffraction pattern from different particles. So, now the question is how do we get the particle size distribution? So, if you look at this equation, basically the intensity at any photodetector is an integrated intensity, integrated with respect to particles, particle size from minimum to maximum particle size, and this is your size distribution that you want to measure, and this is basically a scattering function that you get from Mie theory. So, now this is a problem of deconvolution. So, you have this information that you measure, how do you get this? Or in other words, you find out a size distribution which will satisfy this equation, and that is what is done here. So, there is an equation for this, and then you try to solve this, and then you get the particle size distribution. Okay. But this is not an imaging based technique. But as you can see here, the light that you receive here, it is not only integrated across the particle size, but also it is integrated along the path. So, you see light here from particles which are present, all the particles which are there in this path. So, that is the reason you do not get local information, you get integrated information. So, you get the size distribution, but that does not correspond to a particular location, rather it is integrated one. And this is an example of how this system looks like. So, here you see this is the laser and this is the detector. Here also you can see this, and you see the spray here, though it is not restricted to liquid particles, you can also measure solid particles. So, you get the integrated information. Okay. So, this is the reason why this has to be appropriately used. Now, imagine there is a flat fan spray as shown here. Okay, this is a generic spray they have shown, but flat fan spray means you have a very thin sheet of a spray. So, if you look from this direction, the thickness is very small. So, it is like a plane, the droplets come out in a plane. Now, if you use this technique to measure in this direction, you get good result. But if you try to image from this direction, or not image, try to take measurements in this direction. If this is the spray, if you take measurement in this direction, you are in trouble. In the sense, whatever size distribution you measure, it would correspond to the entire path of this laser beam. On the other hand, if you measure in this direction, the thickness is very small. So, even if you get integrated information, the variation in that direction may not be much. So, you still get some local information. So, this is what we have to keep in mind. Now, typically the advantage of this instrument is its typical size range is very broad. So, starting from 0.1 to 3000 micron you can measure, which is not achievable in the other techniques usually. So, the main advantages of this technique is, as I said, wide measurement range. It is fast, the technique is really fast, even if it has to do this deconvolution process, that can be done very quickly in modern processors. And this is also a non-intrusive technique, and importantly it can work for wet and dry suspensions, and we get full size distribution, not just average as in the case of planar droplet sizing. So, this is quite widely used in industries, mainly because it is very fast, okay, and it is a kind of a plug and play type of device. Okay, it does not require, the technique is quite robust, you can just implement, okay, arrange it and start taking measurement, unlike other techniques like eyelids or PDPA where the alignment is crucial. However, the limitations, as I said, local particle sizing is not possible, and we get integrated information, and sometimes it can lead to wrong conclusions on the shape of spatial droplet or particle distribution as shown here. So, here you have a hollow cone spray. Hollow cone spray means the inside part is mostly hollow because of the way the injector is designed. You can imagine a thin sheet coming out of the nozzle, and that breaks up and gives you this spray field. So, in this case, when you take PDPA measurements, you get this. So, here you see that then the size distribution actually looks like this. Okay, so now if you do integration of the PDPA measurement, then you get this, and this is what is expected in the case of this technique. However, you get this. So, two things. First thing is that if you get this kind of distribution, you assume that it's like a solid cone spray. Okay. Next, the difference in the size. So, that refers to the accuracy. Okay. But this has been improved, but the major problem here is that you get an entirely different distribution and you may wrongly interpret it. This is also suitable for only sizing the dispersed phase. You cannot measure velocity and you cannot get two-phase measurements. Okay, so we stop here. So with this, this module on experimental technique is finished. So we'll start the last module.